The purpose of this video is to go over this trigonometry test review, and we're going to start with the multiple choice in part 1. So we're asked to find the cosine of 5 pi over 6, and we can use the unit circle to find that. The unit circle shows the sines and cosines of all the special angles from 0 to 2 pi, or most of what are called the special angles. And so if we want 5 pi over 6, the angle 5 pi over 6 is right here, so that refers to that point right there. The cosine is the x-coordinate, so it's negative root 3 over 2, so that's why E would be the correct answer for number 1. For number 2, let's move this up here, we're asked to find the cosecant of 5 pi over 3. Now, cosecant is the reciprocal of sine. So if we look on the unit circle for 5 pi over 3, which is here, so it refers to this point right here, the sine of 5 pi over 3 would be the negative root 3 over 2. So we would take the reciprocal of negative root 3 over 2 to get the cosecant. So the sine is this, so the cosecant is the reciprocal of that rational expression. So the reciprocal of that, of course, is negative 2 over root 3, so E is the answer once again. For question number 3, to convert degrees to radians, you multiply by pi over 180. To go in the opposite direction, you would multiply by 180 over pi. So that's why C is the correct answer for number 3. For number 4, if the radius of a circle is r and the angle of a sector is m, you're asked which of the following is the arc length formula. So arc length, if we call A the arc length, it's the product of the radius and the size of the angle in radians. So A equals rm, and D is the correct answer for number 4. For number 5, which of the following is equivalent to the sine of pi over 6? So we could do this by bringing our unit circle back. And so here's pi over 6. So the sine of pi over 6 would be the 1/2. So let's see which of these has a value of a half. So the sine of 3 pi over 4, well, 3 pi over 4 is there, so that's root 2 over 2, so that's not it. The cosine of pi over 3. Pi over 3 is here. Cosine is the x-coordinate, so notice that it is a half. So B would be the correct answer. For question number 6, determine the equation of the function picture to the right. Well, let's start looking at the characteristics of the function. So first of all, the distance, and each unit here is 1 unit. Each block is 1 unit vertically. So from here to here, that's the amplitude, or from there down to there. So that's 3 units. So notice that all of these seem to have an amplitude of 3, so that doesn't rule out any possibilities here. Well, what's the length of the period? The period is pi. And notice that it starts, there's no phase shift and no vertical translation. It starts at the 0, 0 point. So in the absence of a phase shift, we could use a sine graph to model this. So C and E would be ruled out if we're using a sine graph. And you see this one here, if it's just 3 sine x, that would have a period of 2 pi, so that can't be correct. In order for the period to be pi, we would have to have a 2 here. Because remember, to get the period, you take 2 pi and divide it by that number. So that's what gives an actual period on the graph of pi. So that's why D would have to be the correct answer. It has an amplitude of 3, it's a sine function, and it would be 2x here because 2 pi divided by 2 gives a period of pi, which this function actually has. Now I paused the video for a moment and wrote the identity. You're asked which graph this is. This is a cotan graph, and I want to explain why. Cotan, one identity is the cotan x is cos x over sine x. And I'm going to put a graph up here of the sine and cosine functions. Notice that on this graph, the vertical asymptotes are at 0, x equals pi, x equals 2 pi, so all the multiples pi. And this is the graph of the sine function and also the cos function. Notice that at pi, The sine function has a value of 0, also at 0, also at 2 pi. So any place that this has a sine value that's 0, the cotan function would have a vertical asymptote. So that's why there's vertical asymptotes here and here and here. And so that's one reason why this is the cotan graph. The cotan graph, for example, goes up here as you approach 0 from the right side, because as you go along these two curves, the cosine value as you get close to 0 is approaches 1, and you're dividing 1 by a sine value that's really, really close to 0. So something close to 1 divided by something really tiny close to 0 goes towards infinity, and that's why the graph goes up here. As you approach pi from the left side, the cos value approaches -1 here, and the sine value is approaching 0 but positive. So dividing a number really close to -1 by a number that's very small and close to 0 but positive would tend towards negative infinity, and that's why the graph goes down in this direction. So the correct graph for number 7 would be E. In part number 2, you're asked to in number 1 here, convert pi over 15 into degrees. So we would take the pi over 15 and multiply by 180 over pi. One way to remember which way the 180 and the pi go, which one's on top or bottom, is if we're going into degrees and we started with something that has a pi in it, the pi's have to divide out. So that's one reason why the pi has to be in the denominator and the 180 degrees on top. So the pi's divide out. 15 goes into 180 12 times, so all that's left here is 12, or 12 times 1, so the answer would be 12 degrees. For number 2, you're asked to evaluate the following, leaving in exact form only. And so it's the tan of 2 pi over 3 times the sine of pi over 3 times or divided by the cosine of 7 pi over 6. And let's bring that unit circle back again. So there's the unit circle back again. And so in order to evaluate this, so let's do the tan of 2 pi over 3. It's the only one you can't read directly off this. So to find the tan of 2 pi over 3, I would divide the sine of 2 pi over 3 by the cos of 2 pi over 3. So 2 pi over 3 is right here. So the sine is the root 3 over 2. That's what's in the numerator on top, and the cosine, the -1/2, would be in the denominator. Now to take root 3 over 2 and divide it by -1/2 is the same as, or we change it into multiplication. The root 3 over 2 times the reciprocal of -1/2, which would be -2 over 1. The 2's divide out, so root 3 divided by -1 would be negative root 3. So that's why we'll replace the tan 2 pi over 3 with negative root 3. The sine of pi over 3, there's pi over 3, so the sine would be root 3 over 2, goes in there. And the cosine is 7 pi over 6. 7 pi over 6 here is the cosine's the x-coordinate, so we put negative root 3 over 2 here. Now notice this is root 3 over 2 divided by negative root 3 over 2, so when they divide out, that just gives you a -1. So negative root 3 divided by -1 would be positive root 3. So that's the answer for number 2. So let's get rid of the unit circle again here. In number 3, it says to use a compound angle identity to prove that cosine of pi over 2 minus x is equal to sine x. And we need a trig identity for this. So the identity that we need is it says cos pi over 2 minus x. So we would need the cos A minus b because it's the difference between two angles here. And it's equal to cos A cos b plus sine A sine b. Remember, for the cosine, if it's cos A minus, there's a plus here. The sine one is actually the same sign. So if it's minus, it's minus. If it's plus, it's a plus. So cos is the opposite sign here. So we would go cosine of and pi over 2 and x are the two angles. So cos A cos b would be cos pi over 2 times the cos of x. And then plus, and then the sine of pi over 2 times the sine of x. Well, back to the unit circle again. So here's the unit circle again. So the cosine of pi over 2, and I put the degree one on here. Let me get the radian one. So here's the unit circle that we need. And so the cosine of pi over 2, here's the angle pi over 2, and the cosine would be the x-coordinate, so that's 0. the sine of pi over 2 would be the y-coordinate, which is 1. So we have 0 times cos x plus 1 times sine x. Well, 0 times anything is 0, so that's 0 at the beginning. And so we're just left with 1 times sine x, which equals sine x. In question number 4, we're asked to use a compound angle identity to rewrite this expression as one single trig ratio and then find its exact value. So it goes sine cos plus cos sine. So that looks to me like the sine a plus b identity, where we would let a be the 11 pi over 12 and b be the pi over 3 angle. So we're kind of using the identity in the reverse order. We're taking this and simplifying it into one sine. And so this would equal the sine of 11 pi over 12 plus pi over 3. And so in order to add these, we need a common denominator. So I've multiplied this one top and bottom by 4, so that changes into 4 pi over 12. And so 11 pi and 4 pi is 15 pi. So it's 15 pi over 12. And that will reduce because 3 divides into both of those. So we can reduce it to 5 pi over 4. Now if we grab the unit circle again to evaluate, so that's how you rate as one single trig ratio. The sine of 5 pi over 4, well, there's 5 pi over 4 there. The sine is the y-coordinate, so that's y would equal negative root 2 over 2. For number 5, you're asked to determine the exact value for the cosine of 7 pi over 12. Well, 7 pi over 12 isn't on here, so we're actually for this one kind of doing the opposite of what we did for number 4. We need to find two angles that either add to 7 pi over 12 or subtract to 7 pi over 12, one or the other. And I'm actually going to show two solutions here, although there are more, in order to find the exact value of this using sines and cosines from the existing unit circle. So we'll come back to the unit circle in a moment. What I've written here is the angles actually from the first 3 quadrants. So I could have done the 4th quadrant too, but this was enough. And I wrote all the angles from pi over 6, pi over 4, pi over 3 out, etc. And I changed them all to be over 12 because this is 7 pi over 12. If this was like 7 pi over 18, then I'd be getting the denominator of 18, for example. So pi over 6 is 2 pi over 12. I multiplied by 2. Pi over 4, I multiplied by 3 top and bottom, so it's 3 pi over 12, etc. So if we look at all these, we're looking for a pair of angles that add to 7 pi over 12. So the red circled ones, 3 pi over 12 and 4 pi over 12, add to 7 pi over 12. So the add part, we're looking for the cosine. So I would use the cos A plus B identity here. So I'll let 3 pi over 4 be the A, pi over 4 be the A and pi over 3 be the B. So I'm going to write cosine 7 pi over 12 as cosine pi over 4 plus pi over 3. And so in my identity, this would be cos pi over 4, cos pi over 3 minus the sine of pi over 4, sine of pi over 3. And so then we would need the unit circle to evaluate all these. Pi over 4 is here, so the cosine is the root 2 over 2. The cosine of pi over 3, well, that's pi over 3, so the cosine's a half, so a half goes here. Sine of pi over 4 would be the y-coordinate here, so it's root 2 over 2. And pi over 3, the sine is root 3 over 2. And so if I multiply these, root 2 times 1 is root 2, and 2 times 2 is 4, so that would be over 4. And this actually gets a common denominator because 2 times 2 is 4, that's why I'm writing them over the same 4 denominator. Root 2 times root 3 would be root 6. So the exact value for the cosine of 7 pi over 12 is it's root 2 minus root 6 over 4. Now here's another possible solution. Let's put that unit circle up there the other way. If you find two angles that subtract to the same 7 pi over 12. So for example, pi over 6 is 2 pi over 12. 3 pi over 4 we multiplied by 3 top and bottom is 9 pi over 12. If you take 9 pi over 12 and subtract 2 pi over 12, you get 7 pi over 12. So those two angles subtract to 7 pi over 12. So I could use the cosine A minus B identity like this. So my A is the 3 pi over 4, and my B is the pi over 6 angle. They subtract to positive 7 pi over 12. And so putting them in the cos A minus B identity, so we would be the cos of 3 pi over 4 times the cosine of pi over 6, and then plus, and the sine of the same two angles multiplied. So back to our unit circle again. The cosine of 3 pi over 4, 3 pi over 4 is here, so it would be negative root 2 over 2, so negative root 2 over 2 here. The cosine of pi over 6 would be root 3 over 2, so in place of that we put root 3 over 2. plus the sine. 3 pi over 4, the sine would be the root 2 over 2 here, so root 2 over 2 here. And for pi over 6, the sine is a half, so there's the 1/2 substitute in. So this would be negative root 2 times root 3 would be negative root 6, plus root 2 times 1 would be root 2. They're both over 4, so I'm right over 4. Or if I want to write it exactly like this one, I could just reverse it and write the negative root 6 after the positive root 2, and then it looks exactly the same as this one, because they are the same thing. On to question 6. We're asked to prove these following identities. One note here, for B, you aren't allowed, because we're actually proving this identity, you aren't allowed to use the identity that involves the secant squared tan squared 1, which is tan squared x plus 1 equals secant squared x. So just keep that in mind when you do B. For A here, we're asked to prove that cos x times sin x times tan x plus cos squared x equals 1. And so, in order to prove this, I'm going to start with the left side. So I wrote down the cos x, sin x, tan x plus cos sine squared x. And let's put some identities up here. So when you see tans, it's often a good idea to change that to sine over cosine. And so that's one of the quotient relations here. Tan is sine over cosine. So I'm going to change tan x to sin x over cos x. And what happens is and I just wrote this again down separately in the next line, the cosines here divide out. And so we're actually left with sin x times sin x, which is sine squared x, plus this cos squared x. And according to the Pythagorean relation, sine squared theta plus cos squared theta equals 1, so sine squared x plus cos squared x equals 1. And that's what we're asked to prove, that it equals 1. In B, and it's a good idea in trig identities to usually start with the more complicated or longer side and try to show it's equal to the smaller or less complicated side. So again, I would start with the left side here. Secant squared x minus tan squared x to me is a more complicated expression than 1. So that's why I'd start with the left side. So again, I would change tan. Tan is sine over cosine, so tan squared is sine x squared over cos x squared. And secant is the reciprocal of cosine. So I could change secant squared x into 1 over cos squared x. Now notice I have a common denominator. So I could write this as 1 minus sine squared x over cos squared x. And the numerator here, the 1 minus sine squared, if you think of the Pythagorean relation here, sine squared x plus cos squared x equals 1. So if we bring the sine squared x over to the right, or subtract sine squared x from both sides, this would change into cos squared x equals 1 minus sine squared. Well, 1 minus sine squared x is what I have in the numerator here, so that's why I can replace that with cos squared x. It's just a variation of this Pythagorean relation. And so cos squared x divided by cos squared x would equal 1. For C here, this is the identity we're asked to prove. So let's move these identities out of the way here. So we're asked to prove that cos 2x is equal to cosecant 2x is equal to cosecant x over 2 cos sine x. So in this case, I would start with the left side again, although cosecant 2x may look smaller than cosecant 2x because there's a 2x there. That's why I would start with the left side. Not to say that you couldn't start with the right side. It's still possible to the proof. It'd actually be the same proof, just in reverse, really. So cosecant 2x, cosecant, look here, and sine are reciprocals. So cosecant 2x is equal to 1 over sine 2x. And this is how I would change it so there's no 2x anymore. If you look at the double angle identities, sine 2 theta is equal to 2 sine theta cos theta. So I could change sine 2x into 2 sine x cos x. Now, I'm going to break this down into, well, 3 rational expressions multiplied because there's 3 different things in the denominator here. There's the 2, the sine x, and the cos x. So in each case, I could write 1 over 2 times 1 over sine x times 1 over cos x. And if I were to multiply it all together on top, 1 times 1 times 1 is still that 1. 2 times sine x times cos x is still 2 sine x cos x. The reason I want to do that is because you see this cosecant x over 2 cos x has a couple of different parts to it. There's two different trig ratios, and there's also the 2. Well, that 2 is the 2 from the half. The cosecant, I'm going to get that by writing the 1 over sine x as cosecant x, because remember, sine and cosecant are reciprocals. And then the 1 over cos x I'll leave as cos x, 1 over cos x, because I have a cos x in the denominator here. And so if I multiply, see, this cosecant x is the same as cosecant x over 1. So it's in the numerator. So cosecant x times 1 times another 1 is cosecant x in the numerator. And in the denominator, I have 2 times cos x, which is exactly what we want to prove. So that identity would be completed. For question number 7, we're asked to graph a couple of trig functions, one here and then one at the top of the next page. And so the first one is you're asked to graph y equals 4 cos x plus 3. So identify the 4 main characteristics of each function and then use those to graph them. The 4 in front of the cosine would be the amplitude, so it has an amplitude of 4. It's just cos x, so the period is the normal standard 2 pi, has not been changed. No phase shift because it's just x, there's nothing subtracted or added to the x. And the plus 3 means that it's been translated 3 units up. When I have a vertical translation, I handle that first. So here's my 3 units up. And it's kind of like the x-axis has been shifted up to there, and you pretend that this is the x-axis and draw it with the other characteristics. Now this is a cosine function, so the cosine function normally starts at a maximum, the whole amplitude above that line that goes through the middle of the graph. I don't call it a line of symmetry because it's not a true line of symmetry. So 1, 2, 3, 4 units up. Now the period is 2 pi. So notice that my pi here is 1, 2, 3, 4, 5, 6 blocks. So 12 blocks to the right of that point would be another 2 pi. So that's the beginning of a cycle, that's the end of a cycle. Halfway between at pi, it's going to be 4 units below that middle line. And then halfway between the beginning and the middle, which would actually be at pi over 2, it crosses that middle line. And then halfway between the middle at pi and the end at 2 pi, which would be at 3 pi over 2, or pi and a half, it crosses that middle line again. And so there are the 5 points you need in order to draw that y equals 4 cos x plus 3 graph. On to 7b. So in this function, the 2 in front of the sine means the amplitude is 2. The negative means it's been reflected in the x-axis. The 1/3 affects the period, so we divide 2 pi by 1/3. So that's the same as 2 pi times the reciprocal of 1/3, which is 3. So the period would be 6 pi. The pi over 3 here means there's been a phase shift of pi over 3 to the left, and the negative 2 means it's been vertically translated 2 units down. So here's my vertical translation 2 units down. It's also been phase shifted pi over 3 to the left. So what I've chosen here for a scale is I've chosen 3 blocks to be a pi. So another 3 is 2 pi, that would be 3 pi there, 4 pi, etc. So if 3 blocks is pi, then 1 block is 1/3 of pi, or pi over 3. So here's my phase shift pi over 3 left. So instead of starting on this middle line, the y-axis, we shift 1 block to the left. Now the period is 6 pi, so I want to go 6 pi in this direction, and I'll find the end of this cycle. So you see that would be 6 pi right there. So of course the end has been shifted 1 block, or pi over 3 to the left as well. So that would be 6 pi to the right of this point. Now the sine function normally looks like this, but remember it's been reflected in the x-axis, so it's upside down compared to the normal sine graph. So in the middle, where it crosses the middle, would be 3 pi's to the right of this. So this actually would be 3 pi right here. So again, 1 block to the left is the middle. So halfway between here and here, it normally hits a maximum, an amplitude above, but because it's reflected in the x-axis, it'll hit a minimum. So halfway between here and here, notice if you count, well, every pi is 3 blocks, and this would be 3 pi, so there should be 9 blocks. So if you want to count, you can 1, 2, 3, 4, 5, 6, 7, 8, 9. So half of 9 is 4.5. So that's why the minimum here is 1, 2, 3, 4.5 blocks between. And the same thing here, 4.5 blocks to the right of that would be about right there. It almost looks like it's right in the 4 pi. It should be right about there, slightly to the right. And that would be a full amplitude above. So that's what that graph looks like for B. For question number 8, a boat sits 200 meters offshore, so off from a straight shoreline. So there's the straight shoreline. And so here's the boat, 200 meters offshore. Its search beam sweeps along the shoreline. So it's sweeping along the shoreline, going like this, around and around. D represents the distance the beam is from the closest point in the shore. So the closest point would be right here. So right now you see the beam is shining there. So D would be this distance here. You're asked to determine a reciprocal trig equation that relates the 200 meters, the D, and the angle the beam makes with the straight in shortest distance. So in this triangle, this right triangle, for this angle theta, the D would be the opposite side and the 200 would be the adjacent. So the reciprocal trig ratio that involves opposite and adjacent is cotan. So the cotan of angle theta is adjacent over opposite. Remember, tan is opposite over adjacent, so cotan is the reciprocal. And so if we put in place of the adjacent the 200 and the opposite is the D side, then cotan theta is 200 over D. If we want to solve for D, we could cross multiply, and it would actually look like this. If we multiply both sides by D, it would look like this. So the D's divide out. So we have D cotan theta equals 200. And then to isolate for D, we would divide out this cotan theta. So after these divide out on the left, we have this D, and over on this side we have 200 over cotan theta. In B, you're asked to find the exact value of D when the angle is pi over 3. So we need the unit circle again. So here's the unit circle. So for we need to see angle pi over 3, and it's 200 over the cotan of theta. So in order to find the cotan of pi over 3, cotan is cosine over sine. So you need the cosine and sine of pi over 3. Well, the cosine would be a half. Actually, what you can do to make this simpler is I took the 200 and multiplied by the reciprocal of this. So that's why the sine pi over 3 comes on top, multiplied by the 200, and the cosine stays in the denominator. So the sine of pi over 3 would be the root 3 over 2. And the cosine would be the half, so we half in the bottom here. And then the 2's divide out, so we basically have 200 times root 3 over 1, which is 200 root 3. To find the approximate value for D to 1 decimal place when the angle is pi over 3, we just evaluate 200 times the root of 3. There's my calculation in the calculator. And so it would be 346.4. So that would be the distance. For question number 9, you're asked to solve each of these on the interval 0 to 2 pi and answer in exact form whenever possible, whenever you have angles on the unit circle, and otherwise to write answers to 2 decimal places. So the first one is sine x minus root 2 over 2 equals 0, so I would bring the root 2 over 2 to the right side. So we're looking for where sine x is root 2 over 2. And so where is sine root 2 over 2? It's here is one place, so that would be the angle of pi over 4. And sine is also positive root 2 over 2 here, and that would be the angle of 3 pi over 4. Down in these two quadrants, it's negative, so we don't have any solutions down there. Sine is only positive, remember, cast in the first and second quadrant. And of course, this is positive. For B, we have cos squared x minus a quarter equals 0, so bring the quarter over to the right. Take the square root of both sides, so cos x would equal plus or minus a half. And so we're looking for where cosine is a half or negative a half. So we have negative answers here too, negative 1/2 that is. And so cosine is the x coordinate. So notice cosine is positive a half here. That's at the pi over 3. Cosine is negative a half here, so that's at an angle of 2 pi over 3. Rotating around to down here, see cosine is negative a half there, that's at an angle of 4 pi over 3. And cosine's back to being positive in the fourth quadrant, it's a half here, and that angle would be the 5 pi over 3 that goes to that point. So those are the 4 solutions for B. For C, we would have to factor this. This is a quadratic equation in the cosecant function, a quadratic trig equation. So in order to factor it, it goes cosecant squared x minus 6 cosecant x plus 5. So it's really not much different than factoring x squared minus 6x plus 5. We still need to find two things that add to negative 6 and multiply to 5, which would be negative 1 and negative 5. So this should factor into cosecant x minus 1 and cosecant x minus 5. And so if I set this equal to 0 and solve for cosecant x would equal 1. If I set this equal to 0 and bring the 5 over, cosecant x equals 5. Now, the reciprocal of cosine is sine. So whether I'm going to use the unit circle or my graphic calculator, I want to have it in terms of the primary trig ratios, not cosecant or cotan or secant. So that's why I would change this into sine. So the reciprocal of cosecant is sine. So sine x would equal the reciprocal of 1, which is 1. The cosecant x equals 5, so sine x would equal 1 over 5, the reciprocal again. Well, this has one solution on the unit circle. There's one place where the sine function is positive 1, and that's right here. And so that angle would be pi over 2. In order to find the solution for sine x equals 1/5, we would take the inverse sine of 1/5, which in radians is 0.2. So 0.20 is one angle. So that's actually an angle in the first quadrant here. Remember, sine is positive in the first and second quadrants, so there should be an angle over here. And if you subtract from pi, you'll get what that angle is. The two solutions here are supplementary. They should add to pi. And so if we subtract the 0.201 from pi, we get 2.94. Notice if you add those two angles, you should get pi, 3.14. For D, another trig equation that's also quadratic that needs to be factored, and I'm going to use decomposition here. So in order to factor this, I'm going to look for two numbers that add to 5 and multiply to negative 24. 4 times negative 6 is negative 24. And the two numbers that do that are 8 and negative 3. So I'm going to break I'm going to leave the 4 secant squared x alone and negative 6 in the end, and decompose or break down the 5 secant x into 8 secant x minus 3 secant x. And so for the first two terms, the common factor is 4 secant x. So we can factor a 4 secant x out of these two. And so 4 secant squared x divided by 4 secant x would just be a secant x. And 8 secant x divided by 4 secant x would be just 2, because the secants divide out and 8 divided by 4 is 2. The common factor in the end here is just a negative 3. We can factor out of these. So again, we get secant x plus 2 again. So secant x plus 2 is the common factor here. And then when we factor that out, what's left is 4 secant x minus 3. So we set each of these equal to 0. And so this one, we bring the 2 over, so secant x would equal negative 2. For this one, we bring the 3 over and divide it to 4, so we get secant x equals 3/4. Now, that's a reciprocal, one of the reciprocal trig functions again. So we change secant into cosine. They are reciprocals. So if secant x equals negative 2, cosine x would be the reciprocal of negative 2, which would be negative 1/2. 1 over negative 2 or negative 1/2. The reciprocal of 3/4 is 4/3. Now, the cosine function, just like the sine function, can't ever be above 1 unless there's been a vertical stretch, for example, and cos x is just plain cos x. So this does not have a solution because this number can't be above 1 or below negative 1. So we only have solutions from cos x equals negative 1/2. And there's two places that cosine is negative 1/2. And one place is here in the second quadrant, which would be an angle of 2 pi over 3. And then down here in the fourth quadrant, negative 1/2 here is the other place that cosine is negative 1/2. And that's at an angle of 4 pi over 3. Last question, number 10 here. The depth of the ocean at a swim buoy can be modeled by this function, where d is the depth of the water in meters, and t is the time in hours. We're told that t ranges from 0 to 24. We're asked to consider a day when time 0 represents midnight or the beginning of the day. And we're asked to find when the depth of the water is 3 meters. Well, the depth, this is the depth, so we would put in place of d of t 3. And we're going to solve for time. So the first thing I would do is bring the 4 over, or subtract 4 from both sides. So 3 minus 4 is negative 1. So we have 2 sine pi over 6t equals negative 1. And so I would divide this 2 out next. And so we would get negative a half now is equal to the sine of pi over 6t. Next, I want to solve for pi over 6t. So pi over 6t would be, and this is how we get rid of the sine, the inverse sine of negative a half. And so that's where we would look on the unit circle to find the angles for this. So here's our unit circle. So we're taking the inverse sine of negative a half, or looking on the unit circle, where is the sine negative a half? And the sine is negative a half right here. So that's 7 pi over 6. So that's why one solution would be 7 pi over 6. Sine is also negative a half over here in the third quadrant, and the angle there is 11 pi over 6. So that's the other place between 0 and 2 pi that the sine is negative a half. Now, how we solve for t here is, if it's pi over 6 times t is equal to this, then the way I get t alone is I would multiply both sides by the reciprocal of pi over 6, which would be 6 over pi. And so those 6's divide out, the pi's divide out, and I'm left with just t. So I would multiply each of these by 6 over pi as well. So the 6's divide out, the pi's divide out, that would give me just an answer of 7. The 6's divide out, the pi's divide out, gives me an answer of 11. So there's 2 times there that the depth would be 3 meters. Now, what's the period of this function? There may be other places or times in the first 24 hours when the depth is 3 meters. So let's look at the period of this function. Well, the pi over 6 we could divide into 2 pi. So 2 pi divided by pi over 6 would be the same as 2 pi times the reciprocal of pi over 6. So pi's divide out. And we get 2 times 6 is 12. So the period is 12 hours. So to find if there's other times within this day that the depth is also 3 meters, we would add 12 hours to each of these. Because that gives you, it takes you basically from one period into the same spot in the next period. So if you add 12 to 7, you get 19. If you add 12 to 11, you get 23. So there's actually 4 different times at 7 hours, 11 hours, 19 hours, and 23 hours. If you want to go in military time, 700, 1100, 1900, and 2300 hours, or 7 a.m., 11 a.m. The 1900 would be 5 p.m., and the 23 hours would be 11 o'clock at night, 11 p.m. So there actually are 4 different times. So in B, and I've already actually done some of that explaining, I suppose, explain what 0 to 24 represents, and that's the fact that we're talking about exactly one day. The domain this function is defined for is the 24 hours of a day. And there's more than one time a day when the depth is 3 meters because it's a periodic function. I've actually graphed an image from my graphing calculator here. And so the vertical scale is 1, so this would be 3 right here. So there's the 7 hours, 11 hours, 19 hours, that's showing that one right there, and the 23 hours right here. So because it varies from a low of 2 to a high of 6, it actually passes through 3 meters 4 different times during the day. So that's why there's more than one depth of 3 meters in a day. And that's the end of the video.